Questions? So I plan today try to explain some applications of monoidal categories in knot theory. So we have this monoidal. Inside we can say braided, inside symmetric. Yeah, inside it's okay. Basically, it means faithful functor of two categories. Yes, a collection of all monoidal categories is at two category, and etc. Here and here. But um, yes, but you don't really need to see it formally. So braided category is monoidal category with extra function structure and extra conditions. Symmetric category is braided category is extra conditions. Okay, another thing that we have here is um, what is called rigid. Rigid. In fact, we can also here put rigid and here put so rigid braided, and rigid is kind of independent of anything else. But I think we will generally be interested in the braided world, so rigid braided and rigid symmetric. Rigid symmetric. So what is rigid? Rigid means that we have duality. I mean, the good thing about duality is that if we already have a tensor product, then the notion of duality is uh, is a categorical construction. So we don't have to say that we have a functor of duality from the category to itself that satisfies something, but we can actually define the dual object in terms that define the functor that it represents. So if we have x in category C and C is monoidal, and now I hope I will give the correct notations. So what is home from x star to y? So the claim is that this should be by definition home from sig1, the unit, so monoidal category have the unit with respect to tensor product, to x tensor y. So I think this is used like this dual, and in general we might also have another dual, which is defined in the opposite way, home from y to here. No, probably this is a usual dual. I'm probably wrong. This is home from y times x to the unit object. I think this is order.
What do you mean by the unit object in the
So it's
mono?
monoidal category. So in monoidal category, I didn't say it before in details. I just said that there is something like this. So there is unit object together with isomorphisms like this and like this, and it satisfies some coherence relations that related to the associator and all the other stuff. But I did say it in a way because you remember I said several levels of how to define monoidal categories. So for example, I said that you can, instead of saying just tensor product and associator, you can say let's take all the possible tensor product of 2 elements, 3 elements, 4 elements, etc. And they have to all satisfy some coherence relations, so much more relations, but then it's clear that we didn't forget anything. And then there is a theorem that it's enough to define only the tensor product of 2 elements. So if we work in this way, we see that we want to define tensor product of 2 elements, but also of 1 element, which is the identity functor. This will be one of the axioms, but also of 0 elements. Tensor product of 0 elements is functor from um, C to the 0, which is a singleton category, to our category, meaning it is an object in our category. This is exactly the unit object, and all the coherence relations come from there. And the same with the topological definition. You remember we talked about disks, and for any set of the collection of disk in a unit disk, small disk inside the unit disk, we have an operation, and then we say that it's all depends only on the like the big. If we have two paths, if we have two configurations, the path between them, there is isomorphic, and the isomorphism depends on the path, but only up on the homotopy class of the path. And so again, this is true for any natural number of disks, natural in the wide sense, including zero. And if we have zero disks, so we have tensor product of zero objects, it is the unit object. As usual, empty product is one. So, yeah, you can write what what the axiom that the unity should satisfy with respect to the braiding, but you can do it in the minimalistic way, and then you have to think and or to Google it and believe that that they write exactly what is needed. But if you do it maximalistic, so it's already done. We already said everything. So if, for example, we're talking about this small disks. Maybe something I didn't say, when we talk about small disk, in one big disk, you can see that there is inherently here the dimension 2. So you could have do it in one dimension. And then small disk becomes small intervals. And then what you get is, somebody have guessed what you get in that case?
How do you do it again in the intervals inside of this?
So for any collection of k small intervals inside the unit interval, we want an operation of corresponding tensor product. The idea is that we replace the objects that we want to take the product in the small intervals, yes? And if two collections are homotopic, if we're given a path between two collections, we want that the operations will be an isomorphism between the operations. And if two passes are on topic, we want those isomorphisms to be the same. And we have this natural composition thing that if we take one operation that corresponds to one collection, and now another operation that corresponds to another collection, or many. Here we have, say, 1, 2, 3, 4 disks, and now we have 4 intervals, and now we have 4 sets like this of unit intervals and small intervals inside it. So we can place the big one inside the small one and get a new collection of intervals, which will have sum of ki intervals, and then we want an isomorphism between the two corresponding operations. And this isomorphism have to satisfy some very natural coherence relations that look like this, such commutative diagram. Exactly what we did with disk, but with intervals. So do you have any guess what we'll get in this case?
Just an order the monoidal category.
So what does it mean?
The usual
Just
monoidal.
monoidal category that
Yes.
the order depends, because we cannot replace two things. And what happens if we instead of talking about disk, we will talk about balls in 3-dimension? Any guesses?
Symmetric one.
Exactly. Because then all the different kind of reordering things become homotopic. So there is no homotopy. But here one have to be careful. If you will go to higher category theory, then balls will not give you yet symmetric. It will give you higher level of braiding. It's called E3. The usual braiding called E2, and this will call E3. And you can go to higher and higher dimensional ball, and symmetric is what you get in the limit. So it's called infinity sometimes. But since we're not in the infinite category level, still on some finite categorical level, we have only on this level we have only monoidal category, braided category, and symmetric category. And another funny thing that you get here, you remember this theorem saying that a group object in groups, it's a abelian group. And in fact, a monoid object in monoids is also an abelian monoid. And now, we didn't say it, but in general, you can define a monoidal category object in any, okay, this is a little bit complicated, yeah. So two category with some, yeah, in any two category. So monoidal category is kind of monoid object in the two category of all categories. And we can define monoid object in any two category. And the collection of all monoidal category is a two category. And we can define monoid, like monoid object in monoidal categories. Any of you have guessed what we'll get? Somebody?
How do you define monoidal category? The category of monoidal, taking the monoidal objects or
So
the
sorry, maybe I should say it again more clearly. So we define the notion of monoidal category now. So what I said that you can abstractize this and say monoidal category is in fact a monoid object in the two category of categories. So I didn't define the general notion of monoid object in a general two category, but you can guess more or less what it is because the tensor product functor is a functor from C times C into C. So if we have product, and in like in one category we have product, in two category we also have product. So the notion of product of two categories, oh, it's bad phrasing of the categories of a pair of categories, the notion of product of pair of categories. It's the product in the two category of all categories. Um, so in any two category, we might have products. It might exist or might not exist. And if it exists, we can define the notion of monoidal object. Again, you need some more stuff in order to work, but in the similar way that we did in usual categories. And now we can ask what is monoidal object in the two category of all monoidal categories. Do we have guess what it is?
it is depend on how you define it, but it seems like
Yeah, this is why I'm
monoidal
asking for guess.
monoidal categories seems like.
No, but we're already working in monoidal category. So intuitively, it's a monoidal category with additional tensor product structure, which commutes with the previous one, which is a monoidal functor. Yes, it's bilinear. Or no, not bilinear. It's okay. It's monoidal functor from the product. So you remember that in monoids, usual monoids, when we talked about monoid object in the category of monoids, we got commutative monoids. Um, in just a moment, I will close the window so you will hear me better. Um, so do you have a guess what it will be now? Just a guess. No guesses? Okay, so we expect it to be some kind of commutativity. So we expect it to be some kind of commutative monoidal category. Because remember that in group case, in one categorical case, when we have two monoid structures, they become the same and both commutative. And it will actually be the case here. We'll get braided category, but not symmetric category. And the funny thing is that if we want to get symmetric category, we can do it just in one more step. Monoid object in the two category of braided categories is symmetric category. So this is another way to define braided structure and symmetric structure. In this way, it also kind of general, it works in higher language. You will get more and more braided, more high-dimensional braided structure. It's like replacing two-dimensional disk with three-dimensional disk, etc. Okay, so this is almost digression. So now we talked about duality. Um, so no, maybe this is all wrong. No, maybe let's talk only about this dual. And now yes, this dual, and probably the other dual is just when you change the order of tensor product. So I want to kind of ignore the so in general monoidal categories you have two duals, but in braided categories I canonically isomorphic, so I want to ignore this fact. And then in braided category you have some natural map from the, I think from the unit object to here. And rigid category is if you first have dual and second this is isomorphism. So definition, rigid category, it's a braided category. Braided is braided category such that one exists x star, two one from 2x star star is isomorphism. Okay, so we can discuss braided rigid categories. And now begins the fun. The fun saying that we have very nice universal examples like universal, we can consider them as free monoidal category or free something category generated by one object. So universal category with at least one object, like with fixed object. So monoidal category, so the universal monoidal category in one object, let's call it, I don't know, universal monoidal, is just I think ordered no, even don't, yeah, it's very stupid one, just ordered sets, but you even don't have okay, you don't have a set between, okay, it's just boring one, yes, it's just the integers. So universal braided category, this is interesting. So it basically disconnected unit of B Bn. So what is a way to think about it? For each n, we have one object, which you can represent by n points. And morphisms will be braids, so will be passes. So this you remember like this. Etc. But of course, each point has to be connected to exactly one point there. So it's kind of permutation with additional structure. So it's we have one object, and the group of automorphisms of this object is the braid group. And the braid group, you remember, is can be defined in many ways, but one of them is by one of or the set x in S2. S2 or plane doesn't really matter, such that x is so equal to endpoints and distinct points in the plane. Okay, so this was discussed before. But the real, and we can continue here with universal symmetric, which is much less interesting.
What is B?
Bn is a braid group. This B or this Bn?
Both. Bn, you said
This
this is you defined here.
I define, yes, and B is BG, B something. It's a classifying space, so it's a groupoid with single object and group of automorphism. BSN.
So what is the automorphism? What is a morphism here?
So I can consider it as just an element in the braid group, but I can represent it graphically as a braid, as a pass starting, like collection of passes that start with endpoints, ends with endpoints, and the passes I draw them on the plane, but each time two passes intersect. So first of all, they allow only intersect in pair and only transversally. I have to decide whether I go up, above, or under.
This is
And
BN, not the
yeah, so
automorphism.
morphism. So what is a morphism? It's BBN, which means that it is the object is just one object. I represent it by endpoints, and morphism is just element in BN. But I like to think about it like this because then you also see exactly how to compose. If you start with one morphism and then you have another morphism, you just glue them together and you compose them. So this is, and okay, and the main reason is because of the examples that you will see in a moment. So there will be diagrams up to homotopy of diagrams. So when I draw these diagrams, I also can put a new rule that saying that on each like fixed time, I have exactly endpoint. It's a rule here. Yes, it's pi one of these. So it's each fixed time I have exactly endpoints. Sometimes I have like 2 points collide. So, but see, one of them is above and one of them is below. So it's okay. And when we do a homotopy, I have to respect this rule. And I see no, yeah, it is. It does matter. It does matter. Yes. Okay. So this is less interesting, but what is really interesting is it's a universal braided rigid category. And this is already not a groupoid, it's an actual category, and if I have many objects and morphism between them. And what is the idea? That we have at least one object, because, okay, I look at universal generated by one object. So of course we can take its tensor product with itself many times, so we will represent it by several points. But maybe I want to represent this object not by a point but by arrow. Why? Because I also have duality. So I also have several points like this. So this is the way that a general object look like. So it is braided, so I can always assume that first we have only ups and then we have only down, but I also can assume that I have them anyway they like. It doesn't really matter. There will be, like, I can interchange two in more than one way, but I can't interchange two. And what are morphisms? So it's a universal construction. So I basically draw all the morphisms that I have to draw and nothing more. But when you look at what I have to draw, you see that I have some amount of objects. So here I also have several arrows up and several arrows down. And the first thing that you can see is that, okay, I can always connect things like this. I can connect upper arrow to a lower arrow and lower arrow to a yeah, like this, to a lower arrow. So oops, no, I didn't do it well. So I have such morphisms that will look like braid, and each time two things intersect, I have to specify who goes above and who goes below. But also I have two very interesting morphisms that called, I think, unit and co-unit. If I have my object X, the one object I defined, yes. So by properties of the duality, I have one map like this and another map like this. So here one have to be careful. Here it's important that our duality is both left and right duality, which is automatic, I think, in braided category. And you see it by the definition of duality. Yeah, so maybe, yeah, I didn't double check it, so I should have checked. If maybe in the break I will try to check what is the exact correct definition of the left duality and right duality. And so you have both. And what does it mean? It means that each time you have arrow up and an arrow down, which like x tensor x, you can connect them like this. So when you start here, you can go up, but you also allow at some point to go down and connect to, not like this, not like I did, and connect to an arrow which is going down. So when you start with arrow that's going up, you either have to end with an arrow that's going up in the other side of the board, like in the target, or to connect with an arrow going down in your side. And of course the other way around. Which means that that the numbers of arrows downstairs and upstairs does not have to coincide. Or maybe the number of ups and downs, the tot like ups minus down is like have to be constant, but you can take, yeah, you have those maps. Yes, those maps change. Here we have one up, one down, and here we have 0. And the funny thing is that you can also compose this map. You can first perform this one and then perform this one. And then what you will get, yeah, you can compose the other way around, but the other way around is maybe this diagram, which is not that exciting. But if you first do this and then do this, somebody ever guessed what kind of diagram you will represent this composition? With what kind of diagram will represent this composition?
Can you repeat again for the
So
definition of and the rules of composition?
yeah, I am in the process of saying them. Yes, so I'm not saying the final answer yet, but I want to like get to it. So, but the idea is that we only put the morphism that we have to put. So the basic morphism that we have to put. Yeah, maybe okay. Maybe should write it like I should just say it in more combinatorial way. What are the basic operations that we can do? If we have x tensor x, we can have the braiding, which is mapped from x tensor x to itself. Or in general, we have it from x tensor y to y tensor x, but since we're all generated by one element, so the main braiding is from x tensor x to itself, and this we will always represent by this diagram. If we're just using the braiding, we already saw that we can get we'll get the entire braid group. So we have to have for each braid, we have to get a morphism between x to the n and x to the n. So this is one basic thing that we have. Now, if we have x tensor x star, we have such composition. We have such a map between 2 points and 0 points. 2 points, but one with plus and one with minus. Yes, so x tensor x star. And 0 point, which is a unit object, which is represented by an empty set. So this will be represented by such a diagram. And of course, we also have map from the empty set to, say, like this, yes, to tensor x star. So we have this diagram and we have this diagram. And basically we can say, let's use all those 3 diagrams and do whatever we can get with them, with all the compositions, and see what we get. And we can any composition we can try to represent by a diagram. I still didn't say exactly what are the rules of the game, but you see that you can get here many diagrams. So first of all, you can get all the braids. But secondly, what happens if you compose this guy with this guy?
You're getting a loop in the same
Exactly. So you will get braids, but since your arrows can start with, so you will get many passes. But we will things that looks like braids. They have many passes, but the passes doesn't have to go necessarily only up. They can also go down. But at the end, each pass if it started with an arrow up, you have to finish either with an arrow up in the target or with an arrow down in the source. And also you might have several loops that here tangled around all those bytes. And the object that we actually, the topology, so we can define this object combinatorially, yes. Diagrams that composed of all those diagrams, so the compositions, but also we have to be able to do them for like we have the braiding for x times x times x with x times x. We also like have this braiding and the relation between this braiding and the previous braiding. So you can define it combinatorially. It's a bit easier. But also you can define it topologically. And topologically you have very short definition, and of course it's relatively short definition. And of course it's a non-trivial theorem that those two definitions coincide, and what you actually define is a universal object. Yes, it's a braided rigid monoidal category, which is initial with a marked object, which is initial object in these two categories. And now I will try to give the topological definition. And for this, I want to define the notion of tangle. So in general, what is a tangle? It's something rather simple. It's let's do it like this. It is a collection of gamma 1, gamma n, and mu 1, mu k, such that gamma I is mapped between the interval and T3, a three-dimensional disk. Gamma mu I is a map between S1 to the three-dimensional disk. But here I have to take the interior, so it's map S1 into the interior of the disk, and gamma I have to respect the boundary. Yes, so the boundary of the interval have to go to the boundary of the disk. So we have the three-dimensional sphere, and so there is a tangle there. So we have strings that's starting with one point on the sphere and ending with another, and also there are several loops inside. So this kind of generalization of the notion of link. Yes. Everybody knows what is a link? Who don't know what is a link?
I don't know.
So what is a knot? Do you know? A kesher.
Yes.
Yes. So a link is a simple generalization of knot. When in knot you have just one immersion of S1 to the three space, like one-to-one map, continuous one-to-one map of S1 to the three space, to R3. In link you have several maps like this, and they don't allow to intersect. Yeah, I forgot to say, tangle also, all the maps are one-to-one, and they do not allow to intersect. The images are disjoint. So
How is it related to mu?
so the mu's are also one-to-one. They have to be, the mu's
No,
together are a
to the link.
link. What?
To the link. The gamma I
Ah,
is what
so
is the
a link is where you have only mu I and don't have gamma I. Yeah. And of course, you see that any braid gives you a tangle because you can put your braid in the box. Yeah, the braid starting with endpoints here and endpoints here, and things goes like this. So you can bound it in box. So it should be done in three-dimensional space because strings can go over or below each other. You put it in a box, you get a tangle. But there are much more tangles than braids. Any link also give you a tangle without beginning and without an end. So now when we have tangles, so this is tangles with n endpoints. So now I want to define, okay, I want to define this. So, sorry, object of universal braided rigid category is just pairs m comma n. Okay. N square, yes. And now I want to define morphisms in this universal. Oh, yeah, okay. Um, so what I do, I say I have two pairs of numbers. So morphism, so here between xy, the pair xy and the pair ab. So I think about xy like a x beginnings, x arrows that going up and b that going down. So x arrows that going to be the beginning of my string, and y arrows is going to be the end of my string. So what do I want? I want that each arrow that starts here have to either end in y or in a. So what do I get? So I want that x plus a will be equal, no, x plus b, sorry, will be equal to y plus a. So if it's not the case, then there are no morphisms. There are no ways to connect things. So otherwise, I put empty set. And if it is, then the answer is very simple. I just take tangles of this size, x plus b, up to equivalence. X plus b, which is the same as y plus a. And geometrically, how do I think about it? I think about it as such diagrams that look like braided diagrams, but they're a little bit more complicated because things can also go down, and also there are loops there. And I start with those points and the arrows that going up, and going down. And so I have all this picture, and now I just put it inside a box. So from the sides, I go far enough, so and I put box, and I have downstairs and upstairs, and you see that there are many points in the boundary of the box. Some points with arrows up, and some going with arrow down, but some arrows going like inside the box and some going outside the box. But the total of going inside the box have to be equal the total going outside the box. Yes, each arrow that starts outside have to go. Oops, yeah. Just a moment, I would correct myself, but have to go out. And also I have several loops inside. So I take all the tangles like this. So maybe here I have to be a little bit more careful when I define the tangle. So yes, I was careful, but by luck. So I talk about tangles with n strings, and the number k is not fixed. It can be any number. So tang n is all the tangles with n beginning points and end points, and any number of closed strings. And then this works. And how you compose two tangles? So here it's important. Yeah, maybe. Yeah, okay. This is a set, but you have to also give names to your y. Yeah, so each of the points in the end of the sphere should be labeled by, say, number from 1 to n, which might be points that going inside and points that going outside. And so, yeah, some of them label, say, the points that going outside would be labeled by numbers from 1 to x, and the points that going inside will be labeled from numbers x plus 1 until x plus y. And then you use those points to compose two tangles. Just remember that those tangles can be thought of as box, and then you have beginning and end, and you just compose them. So is the definition of this category clear? UBR? A topological definition. Maybe I can say it slightly differently. So Objects are pictures like this. I have n arrows up, some number of arrows up and some number of arrows down. And morphisms are boxes. When you stick one object here, like the arrows here, and one object here, and then you pick up any tangle that you want that starts with those arrows and ends with those arrows. And of course, everything is up to homotopy. So now is the definition of this category clear?
And what is the tensor again? How you propose?
Good question. So tensor is just concatenation. Yes, I have one picture of arrows up and down, another, and just I put them one next to the other. Yeah, so of course, in order to work properly, I don't want to. Of course, I can. You know, yeah, it's better to say that I don't care where they are. They don't have to be ordered like this, at first up and first down. They can be any point in the plane, and then you can just put them to the right and do the composition. And of course, everything defined up to homotopy. So this is very nice. Of course, there is something to prove here that this tangle category is actually the universal. So I define the category, but I have to prove that it is universal braided rigid category. And okay, it is true. It is a theorem. It's not very simple. It has some topological content inside it, but basically most of the content is this Sart's theorem or yes, this transversality principle that as usual you have this topology and it can be very complicated, but so you can always start with the complicated topology and make a diagram out of it by projecting it to some plane, and then remember each time you have an intersection who goes below and who goes above. In principle, you can have triple, quadruple, and whatever intersections, and then you will be less happy. But but you can always pick up a generic plane. First of all, you have to perturb your passes a little bit so it will be very smooth, and then you can pick up a generic plane and project there, and then all the intersections are transversal and only in pairs. But then you have to go to the next level. What happens if you have a homotopy? Why each homotopy you can make as a sequence of some simple operations, and once you see it, you can write everything in combinatorics, and then you see that this combinatorics is basically the axioms that we have for braided category, for rigid category, for monoidal category, and whatever. So it's a lot of work. It's not an easy theorem at all. But on the on the philosophical level, it's somehow expected. And if you choose the definition of braided category correctly, then probably it becomes much easier. Okay, let's take 10 minutes break. Any questions for the break? Okay, try to find out exactly what is a right dual and left dual and how they related in rigid category, but I did manage to do it in this 10 minutes, so I will just send you material afterwards. Um, yes, it's not, it's written in lab, but maybe not all possible details. So I have a better source. I will send you a book, a better source. Questions? Somebody is back? No one is back? Oh. Navanetta is back. Tal is back. Ah, you even here in the institute. Oh no, me, Kate. Itai.
I'm here.
Good. And Jakob and Lior. Jakob here, I see. And Lior is here. Great. So, I need also to switch on to tablet, the screen sharing. So where were we? So we define this category. And now, nice thing happened. So what is, in this tangle category, what is automorphisms of the unit object? Guesses?
Only identity.
So we start with tangles that like have nothing up and nothing down. So of course we have identity, which nothing up, nothing down, and nothing in between. But can we still put something in between if we have nothing up and nothing down?
All permutation of it, maybe?
Permutation of what? We don't have anything points down and anything point down up. So it's like permutation of zero elements. So it's just identity, as I said. Our braids of zero elements is also just identity. But now we're talking in tangles, in this rigid monoidal braided category with one generator. But we don't look at the generator, we just look at the trivial object. But still, the fact that there is another object there gives us some automorphism, non-trivial automorphism of the trivial objects. We even discussed one of them. We have the unit and conunit. We have like 1, x tensor x, star 1. So this is an automorphism of the unit object, which is something, yes? So in what diagram would represent it? Do you remember? You said before, what diagram represents this morphism, this composition?
No, I just didn't understand well the morphism. So, what is
so morphism between two. So the object in the tangle category is a collection of points in the plane with arrows up and arrows down. And morphism between two objects are tangles, which you can put in a box. You start with one collection and with another collection. You have to be compatible with the arrows, and you also can add as many loops as you want in between, and everything should be bounded in a box. And the tangles are, you care about them only up to homotopy. The points in the plane, you can say that you care about the actual points, but of course, when you move the points, they become isomorphic because you have the tangles that connect them. So what are the automorphism of? So what is the unit object? You remember, yes? It's just one. It's just empty set. So what are tangles that start with nothing and end with nothing?
the interior links?
Just the links, yes. So to be more accurate, oriented links, there is a difference between links that going this way and loops that going this way. Those two loops are of course the same because they are homotopic, but if you start to link them one into the other, you get something a little bit more complicated. So this is interesting objects, say from algebraic topology, from low dimensional topology, I don't know. And now it kind of got arise naturally in category theory. Of course, the fact it arises naturally, the fact that this is somehow universal object is meaningful fact. It's not tautology, but it is correct. So now assume we have some monoidal category. See with tensor product. And now assume we also fix some object x in C. So since we said that this universal rigid braided category is actually universal, and once we fix here object, we have a functor, a unique functor like this, which means that we have a map between links, between oriented links, and automorphisms of the identity element, which is kind of nice. We get invariant, an actual, or maybe not numerical, some interesting invariant. So example, C is equal to vect, and x in C is equal to vect say over C, and x in C is equal to some specific vector space. So we will get a map between oriented links to, any guesses?
Where X plays a role here. You define it from category to category.
So this is universal category on one object. So the point have to be mapped to this object X. The generating object of this have to be mapped to X. But you're right that in the answer it does not play any role because it's automorphism of the unit object. So what is the automorphism of the unit object in C?
All the basis elements, all the possible
What is the unit?
independent.
What is the unit object in C? In vect, sorry. Yeah, in C, in our C that's equal to vect.
The field itself?
C. Yeah, it's vector over C, it's a complex numbers. And what is its automorphisms?
It's only identity if you fix the C, if they are still linear, right? Or no, sorry. Not sure.
Just C. Yeah, multiplication by any scalar. Which is nice. So we got a number. So this number in particular is kind of boring. It's just the number of components in the link. So exercise examples. So exercise computes this. Exercise compute. And you see it's very boring. But now you can change it a little bit. You can consider C to be the category of just to be representations rep, say, or finite dimensional rep of GLN or SLN. Well, let's do GLN or just a group GLN. It's more or less the same. And so this is a nice tensor category, and here you can take X to be the standard representation, like CN standard representation. And then you get some interesting number, which depends on n. So it's important that this n and this n is the same. And this number depends on n. And maybe I'm wrong, but I think it's called the Jones polynomial. So it depends polynomially on n. It's something to prove. And it's called the Jones polynomial. So you got some non-trivial link invariant that I'm pretty sure was known before, but yet. Yeah, I think both of them was known before, but the most general one was known before, but not much before, and it's kind of triggered all these procedures, as far as I understand, or they just made it simultaneously. So the most interesting one is what happens when you still kind of stay in the universal world, but you put more conditions. So before we had just universal monoid like braided blah 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 category with one generator, but completely free. We had this just one object x, which we represented by a point, and we just did not care. So now we want to put some conditions. So first thing that we want to talk about is dimension, or even before dimension, trace. So definition, let C be a rigid braided whatever category. Let x in C and phi from x to x. So although general category does not have to be this universal one, but still we can use diagrams to represent morphisms in general category, but no, of course not all of them. Some of them will be just some morphisms that in this category, but we still will have the braiding and have the unit and co-unit. And the way to do it, you just use boxes. Yeah, so you have this x, and you have this phi, and you have this x. So it's a map from x to x. But you can have different kinds of things. So for example, you can have here x star, and you have here the co-unit, which is a map from identity to x times x star. And you have here the unit, which is a map from x star times x to identity. So overall, when you do this thing, it's just another way to write the unity x star times x x star times x, and here we do like identity tensor phi and unity. So this composition anyhow is element in endomorphisms of one. Or before I wrote automorphisms, I wanted to write endomorphisms. I'm really sorry. Endomorphisms. So it's not necessarily a scalar, but in many categories, so sometimes it's even like additional assumptions that endomorphism of the unity is the field that you're working over if we're talking in some additive category or something like this. So this is defined to be the trace of phi. And exercise prove that in vect trace is the usual trace. Yeah, it's rather simple that this is one of the ways to define trace. So you have to understand what is a unit and what is a co-unit. It's also rather simple objects in vector spaces. So you have map like this and like this. The duality is of course just the usual dual space. So once you prove that the trace is a usual trace, so you also can get the corollary. The trace of identity is dim V. And now in general definition, dim x, x in C, is defined to be trace of identity. Here the corollary is in vect, and the definition is general. So in general monoidal category, you have a notion of dimension, not monoidal, rigid monoidal category, but this dimension is not an integer, is element in endomorphism of the unit object, which is also often the field over which we're working. So say we're working over complex numbers and everything is like C linear and additive. So we're working over C, and we often ask as additional axioms that endomorphism of the unit object will be just the field over which we're working. We get a complex dimension, so we get objects with complex dimensions. So now we can consider the universal braided rigid category, but not just free with some object x which can be whatever it wants, but with this relation that dim x is equal to t. We can fix some number t, and we can consider this object. And another thing that we can do, we can consider what happens when we do the braid square. So it corresponds to diagrams that look like this. Yeah, so braid is automorphism of x times x, but we don't really expect it to be a scalar or something simple because it actually changes the places of two things. Even in vector, it's not a scalar. But if the category is symmetric, then braid square is by definition equal to 1. So we expect to be able to control braid square, and we can ask that braid square will be equal to q when q is some number. So we can do it with some fixed numbers, but there is another trick. Sorry, what do I mean by numbers? So we just started with some free category. There are no numbers. We're not working over C. So first thing that we can do is to linearize. So we can linearize over C. And what does it mean? So if we have a general category, we can linearize it done by two steps. First of all, we want to make it additive. In order to make it additive, we make the number we just includes artificially direct sums of many objects, like of any set of objects in the category. We just add the sum, and also we change the home. We change like home. We have some category C, and we C linearize it. So this home become span, the C span of the previous home, like the home in C, between x, y. So a general procedure starting with a general category and just force it to become an additive category. And so we can just, if we would do span over z, then we get a general additive category. And if we do span over c, then we get C linear category. C linear category is additive category, such that on the home we have further a C linear structure. So we can just C linearize the universal braided category. And then we can add those two relations. That x is equal to t, dimension of x is equal to t, and the braiding square is equal to q. Now we usually want to change it a little bit. Before we change it a little bit, we want to say it more universally, not to fix the values of x and q, but consider them in a family. And there is a general algebraic trick what you do when you want to consider family of vector spaces, categories or whatever. You just do it, instead of doing it C linear, you consider it linear over some ring of polynomials. In this case, in two variables, t and q. And now t and q stop to be some specific numbers in C. They become the generators of some just abstract parameters, which are the generators of this ring of polynomials in two variables. And yes, and this is it. So you linearize over this ring, and you put those two conditions. So it becomes a universal braided rigid linear category, such that the dimension of the generator is some parameter t, and the braiding square is some parameter q. So now warning, t and q are usually replaced, or maybe t and q are bad names, so maybe I will call it t prime and q prime, and t and q are usually some other two parameters, which can be expressed via t and q, but not polynomially expressed. They can be expressed as a power series. So it's not completely equivalent to this. It's become equivalent to this if we go instead, I think, and write. Yeah, so in T everything is dependent polynomially, but in Q it's power series, just formal power series. But for this level of discussion, I don't really care, and maybe I'm not 100% sure that they are right that they're doing it. Maybe they could have done it
Um,
with those parameters, the dimension and the Q. Yes, Guy, you want to say
yeah,
something?
I mean, when you do the linearization over
Mm-hmm.
CT tag, Q tag, Q
Mm-hmm.
prime, do you add any objects?
Direct sums, only direct sums.
So, I
At the
mean,
I
for
can add
whatever,
more, but I start with only direct sums.
so how can, I mean, one dimension stay the same?
What?
One dimension stay the same?
So the question is, what is the dimension of the generator x, the one object that I start with? Before, the dimension of x was just the link circle. It was not any number. It just was an element in automorphism of the trivial object, which is a circle.
Yeah, but I mean,
Yeah. So it's not
where will,
automatic thing. It's not. Yeah.
how will an object with a dimension which is t prime can appear?
So it's the general. It's an abstract object which is denoted by one point, and its dimension is the abstract automorphism of identity, which is denoted by a circle.
Oh, okay.
But now I add an additional relation. So those things that are written here
Okay, okay.
upstairs are not some automatic things. I could, if I would not write them, I would get some other category, which would be not a bit more interesting, or almost not a bit more interesting than the original category of the of tangles. It's just a linearization of the original category of tangles with those coefficients, which means something stupid. That an object is tuple of tangles, and a map is a matrix of tangles, and each tangle also can, it's not just one tangle, it's a combination, matrix of combination of tangles, and the coefficients will lie in this ring. So this is stupid
Oh,
and not interesting at all. But this allows you to quotient by some additional relation. So I didn't, okay, we more or less describe the general notion of quotient of a category by not a subcategory, but some collection of errors by relations on the morphisms, yes? So now I have a new automorphism of the identity object. I have the scalars, yes, because now I
mhm,
allow matrices, so I have just, yeah, it's like scalar times identity. Sorry.
mhm.
Yeah, so t means t times identity in the identity object. In the unit object, I have links, but I also have the identity map, which is just the empty link. And now I can take the empty links 5.5 per time. And now I just say that I can replace circle and the empty link with the number 5, like the empty link 5.5 times, or with the number t, whatever, which is not a number, it's just parameter. But I could have just fixed the number t, but it's more interesting if I just make it an abstract parameter, more general. And this become much smaller categories, have much less morphisms. And now theorem is that in this category, endomorphism of the unit object is just this original ring, C, TQ. Or what power series or whatever, like with the primes, without the prime, it's just a matter of taste. Probably the theorem will be correct in only one formulation. What is clear that it is quotient of this ring. And this is rather easy theorem, because now you start with any, it's not clear, but it's easy, yes? Why? Because in general, in the original category before the quotient, the endomorphism of identity was just links. And in this category, the endomorphism of identities should be formal combinations of links with those parameters. But now we're allowed to do some operations because we have some equivalence relation. We know that each time we see a circle, we can erase it and just multiply the link that is involved in with the number t. And also, each time when we see something like this, מעל, מתחת, yes, something like this, we can like take them apart, like replace it with a thing like this, but the price will be multiplication by q, not q squared, with a q. But again, it's not really q, it's q prime. Yes, so usually people use q for different things. But what does it mean? Now you draw any link, and now you can just tear it apart. Each time you see some problem, you just tear it apart and you pay the q prime, you don't care. And after you tear everything apart, you get a bunch of circles. But each time you see circle, you just erase it and pay the t. So everything become equivalent to scalars. Each time different scalar, but scalar. And so this is not the way it's usually done, because in this way it seems that everything links become equivalent to monomials. And the way after you do the change of variables, the links become equivalent to polynomials. And of course, it's not clear that the process will give you a unique scalar. And if it will not give you a unique scalar, it means that two scalars have to be equivalent. So when I say scalar, it's not really scalars. In this parameter, they have these parameters t and q. So we will have some quotient here. But the theorem is that when you do everything correctly, you're not working with q and t, but you're working with q and t and not with q prime and t prime. When you do everything correctly, you actually not have to quotient by anything else. You get this ring and not any quotient of it, or maybe power series, but yet it works. I think you actually can get the entire ring if you work with the correct parameters. And this is very nice category. It's a universal. So the universal braided rigid category, C of t q linearize under those conditions, dim x is equal to t prime, which somehow depends on t, and dim and braid square is equal to it's not exact. There are some other changes. Okay, it's approximately to some other change of variable. So instead of no, it's okay. Probably you can do it as is. No, you want some change of variables, some more delicate change of variables that relate to the braid itself and not only. Okay, what I'm saying is approximately correct. This is very so we put it like this. Very nice category, which is closely related to the category of representations of UQGL. Rep of UQGLT. And now I have to explain what I'm talking about. So if you have a Lie algebra, everybody knows what is a Lie algebra? Somebody don't know what is a Lie algebra? Good. So if you have a Lie algebra, you have the category of its representations. And you also have the universal enveloping algebra of a Lie algebra. Everybody knows what is a universal enveloping algebra of a Lie algebra?
No.
No. So basically the idea is, okay, in the language of category theory, I can say it very simply. You have a functor from associative algebras, like actual algebras that have associativity, yes, to Lie algebras. And this is just taking algebra, and you have the commutator AB minus BA. This is a Lie structure. So this functor have an adjoint functor. And this is the construction of universal developing algebra. But the idea is that you take a Lie algebra and just make it by force a universal an associative algebra. So it means that any two elements in the Lie algebra, you have to be able to take their product. But you don't have any given product, so you just add it artificially. You take all expressions that look like products of elements in the Lie algebra and their combinations, but you add one important relation. AB minus BA is actually the commutator if A and B are elements in the Lie algebra, so it's actually the commutator in the Lie algebra. Yeah, so you take the free algebra generated by the elements of your Lie algebra, but of course you want the addition to respect the addition, and the commutator to be the actual commutator. And now there is the notion of representation of the Lie algebra, and there is also the notion of representation of the and by more or less by definition, it is just representation of the universal developing algebra. And this player Q, which means quantum, but also Q is actually a parameter, it's some modification, some deformation of this algebra that should be kind of sort of as a quantum version of GLN. So this we can do with GLN, but maybe I should write prime because it's not really correct. This we should do. This we can do with GLN. But now I didn't write here GLN. I wrote here GLT. So if t is integer, then GLT is actually GLN, and I can consider the category of representation of GLN. And what happens if t is not integer? So the thing is that we don't really have, of course, matrices t by t when t is not integer, but we do have the right-hand side. So you more or less can take this as a definition of representation, of the category of representation of a group that of course does not exist, or of Lie algebra that does not exist, of Lie algebra of t by t matrix. And moreover, its quantum version. So you can take q equal to 1, and then you get the classical version without quantum anything. Yeah, so this is kind of very abstract object, and I can try, or I of course cannot do it now, but you can try to define it in some other ways. But basically, if you just interpret this as a definition, so you got the definition of this very abstract object, and the only thing that you actually have to check that when q is equal to 1 and t is equal to an integer n, then it actually works. And the truth is that it does not work. So when you plug in q is equal to 1 and t is integer, you get category which is closely related to the category of representations of GLN, but it is not that category. So first of all, it's not abelian category in any way. It's not even close to be abelian. So the one thing that you have to do is what's called Cobization. So unfortunately, there is no general procedure that starts with a general additive category and just make it abelian, just free abelian construction. This does not work. But there is a way to make it what's called Korubian. Korubian category is category. So abelian is where all maps have kernel and co-kernels. And Korubian category is only maps which are idempotent, maps which square equal to themselves. So those maps should be thought of as projection to subspace. So they actually should split your space into not only, they doesn't only have kernel and co-kernel, but basically you split the endomorphism of an object. They split this object to a direct sum of its image, of the image of the idempotent and the kernel of the idempotent. So they have to split it to direct summand. But of course, if your category is not abelian, in general, the kernel and the image does not have to exist. But if you assume, so Korubian axiom, the Korubian category is a category where you do have kernel and co-kernel. And there is a general procedure starting with any category get the Korubian category. And the nice thing here that if you apply this procedure to this category, you will get usually an abelian category. Usually, except of the cases when t is integer. So in case of t is integer, you will not get an abelian category, and therefore you will not get representation of GLN, but you will get something we get the functor to GLN, to representation of GLN, so you can think about it as some version of the category of representation of GLN. But why do I tell you all of this? In fact, I should have, yeah, I can, yeah, here, even in this, after this theorem, you already see something very interesting. So even if you don't really know what is this category and how to think about it, so now I gave you kind of hint how to think about it, some quantum and non-integer version of the category of representation of GLN. But even if you don't think about it like this, you still have a category, and you have a functor from UBR to this UBR with all pictures here. And so you have a map between oriented links and endomorphism of identity here, which is just polynomials in two variables, t and q. So it means that for any oriented link, you get a polynomial in two variables. And this is much better than just get a number. And this polynomial, I think, has a very funny name, Homological polynomial. So those are all letters. They are initial of different groups of people that go to these polynomials from different directions, approximately in the same time. It's rather recent, yes. It's kind of 80s, I think, or something like this. Though this definition looks extremely abstract, but when you compile it, you get something very simple that you could have done, like, after you know it works, you could have done it in the 19th century, or even earlier, because basically what you do, you start with a link that looks something like this. And then each time you have an intersection, you allow to replace this intersection by this intersection. But you have to pay some price, and the price is just not intersection at all. So alpha plus beta plus gamma, this is called skin relation, I think. So have to be equal to, I think, 0. So you take your link and you decompose it to 3 links, and their sum is 0, so you can take one of them. So you can replace this by some combination of this and this. And both of those guys are simpler. So of course this looks simpler. This is not necessarily simpler, but you will do it not for arbitrary intersections, but only those that you want to actually replace. And so your link becomes simpler and simpler, and at the end, your link becomes just circles. But of course, it becomes not one link because there's each time sum of 2, so you have sum of several circles. And there are some coefficients there that involve the letter Q also, not only the letter T. I think that even those coefficients involve only the letter Q, and then in the end you have several circles, and each circle is just T. So several circles, n circles is T to the n. So after you do all this operation, you get a polynomial in T and Q. And of course, it's completely not trivial that you will get that your resolution, like the polynomial that you will get, will not depend on the way you resolve your link. Yes, you start with a link diagram and you break it down to pieces, but it's not very hard to prove. After you found the correct alpha, beta, and gamma, it's not very hard to prove. And I don't know the exact story whether they found the correct alpha, beta, gamma by understanding this game, or whether they did combinatorially. I think it was some combination. So I think it first appeared without the categorical explanation, but probably the categorical explanation was nearby. They kind of had it in mind, but not exactly. And now you can, soon after those so several groups did the work, you can interpret this polynomial as a result of this functor, which is kind of abstract functor. You start with a free category and free by rigid category and map it to some specific category and get a polynomial. And this is very nice. Any questions? No questions? Okay, now I have a dilemma. I wanted to say another thing about monoidal categories, which will, if I want to do it well, or at least not very badly, it probably will take more than 5 minutes, but I can somehow squeeze it to 5 minutes or 10 minutes or something like this. On the other hand, I can spend 10 minutes about the things that I just did not say in this course and some themes that are there, and maybe we want to discuss them. So what do you prefer? Or maybe the third thing that I can do, just stop because maybe it's too much. So since nobody is saying
I
anything, so
prefer
yes,
the
yes.
second option.
Second object is general thing. Great. Yeah, just I wanted to say that anyone that will say he will be 100% of the voters, so he, yeah, he will decide. So very good. Second option. So yeah, I think what I wanted to say is somehow related to higher categories. Let me see whether not teaching. I wanted to talk about derived functors. Okay, I want to talk about derived functors, and I wanted to talk derived categories, and I wanted to talk about a higher category theory. So derived categories, I said something, yes. So for any category C, we defined, or at least try to define the derived category, the category of complexes. And I can say now about derived functors. So in a sense, this procedure of derivation of category is functorial. So once we have two categories C and D, and functor between them F, we can expect to get a functor here. So of course, this is not, it's not always the case that we can do it, but under reasonable conditions, we can do it. For example, okay, well, depends on your definition of reasonable. So there is no one good procedure to do it. It works only if f is either left exact or right exact. And then you can define its derived functor by properties. And of course, it doesn't have to exist. I think it's always unique, or maybe even this is not the case, but under reasonable conditions, it's unique, and under slightly stronger conditions, it exists. And how you think about it. The idea is that you measure how much your functor is not exact. So it's exact from one side, but you measure how much it's not exact. So you start with a short exact sequence, x, y, z, and it goes, say it's left exact, so it goes to x, to f of x, f of y, f of z. So this is exact, but if I will put here 0, I will get something which is not exact. But how not exact it is, it appears to depend on x, which is rather, at the first point, it look weird, x is far away, but then if you think about it, it's not that weird. Because say x is injective, it can also be done in the other side, projective. Then this sequence splits to a direct sum. And if this sequence is a direct sum, then x have no, then it goes to an exact sequence. So if x is extremely nice, then you expect it to go to exact sequence. And what happens in general that here you will have the first derived, it's called, it's probably right derived. So the first right derived functor of f applied to x. So maybe I will write it here. R1 of f. And you can continue further and further. So the first approach to derived functors was that if you start with a functor which is not exact, but only left exact, say, then often you have a sequence of functors that measures together how it is exact. So derived functors was not just one functor, but was sequence of functors. But then after you know about derived category, you can consider it as just one big functor between the derived categories of C and derived category of D. And you remember that C lies here, just complexes with only one non-trivial object. But, and D of course also lies here, but C will not go into D. It will go still to the derived category of D. And how you think about objects in derived category of D? You think about the, by definition, complexes, but you kind of care only about the cohomology. So yeah, you have very nice functor from here to just graded objects in D. So just direct sum of many, many copies of D. And this is exactly that sequence. But when you look at this picture as a derived functor from one derived category to another derived category, you get more information. So this is a very powerful tool in homological algebra. I think the notion of homological algebra existed before, but before derived functors even, but just in examples here. So in many cases, you measure some non-exactness or something that kind of, it's often called abstraction. So something that locally does not happen. So in some simple cases, that does not happen. But when you go to the complex case or the complicated case, you see that some things you cannot resolve. It's like homologies in topology, or like non-exact of a functor, or like something which is extension of two objects, but it's not the direct sum. And when you try to measure how much it does not resolve, this gives rise to notion of homologies, cohomologies, and derived functors, and all this topic is called homological algebra. And uh, today not modern, but like the second stage of homological. So maybe the zero stage of homological algebra was people defined homologies in some situation, like homologies of group action on some representations of groups, etc. The first step of homological algebra was to define derived functors for some functors, and yeah, so two functors which are very often is very interesting to derive is the functor hom and the functor of tensor product. Hom is a functor of two variables, so you can derive by each of them, and tensor product, it's okay. Let's talk about some usual situations. So it's symmetric, so you don't really care about who you derive. But hom, you also, it happens to be that you don't care about who you derive. So here you get X, and here you get Tor. So those maybe are the first two players of homological algebra. But then you can, but when you derive them like this, so Tor I and X I are like sequences of functors. And when you derive them in the more modern language, you get R hom and the left, like this left derivation of tensor product. So those are like one functors, but from the derived category to the derived category, or in those both functors of two variables. So take two objects in the derived category and get a third one in the derived category. But of course, there are many other functors. And maybe the next stage in homological algebra is to reinterpret or redefine the notion of the derived category. And the thing is that derived category is probably not a good way to think about it just a category, or as a category at all even, but rather as an infinity category or some higher version of a category. And the reason is that when we go to the derived category, what we actually say, we say, okay, we have the same objects, it's good. But then we add morphisms, which is also kind of good. But when we add the morphisms, how we add them? We add them like these zigzags or heads, or if we have our own conditions, or if we want to do it in one step, like this zigzag. But when we see that we add this zigzag, we see that sometimes two zigzags have to be equivalent. So we quotient out by equivalent relation. And in category theory, in higher category theory, it's never a good idea to quotient out by equivalent relation. Each time you have two things equivalent, you want to remember why they're equivalent. There is some reason why they're equivalent, and you want to incorporate this reason to the object. So instead of quotienting them, you say, no, they're object in a category, and the fact that they're equivalent just means that there is isomorphism between them, and they might be equivalent in more than one way. Then there is more than one isomorphism between them, or more than one morphism between them. And there may be many morphisms like this, and sometimes two different ways of equivalence also can be thought of as just one, as equivalent ways. But again, if they're equivalent, you don't want just to think of them as the same, but you want to understand why they're equivalent and to say that you have no morphism between morphisms. And you kind of force into talking about this higher and higher categorical level, and you force into talking about infinity categories. And here there is something that comes to help, that except of the first level, your category itself, where you have morphisms which are isomorphism and not isomorphisms, at least at the first glance, all the other morphisms that you add, you only care about morphisms, the only isomorphisms. The only reason why you added them is because you wanted to say that two things are equivalent. So when people say infinity category, they often mean what other people call infinity one category. So infinity one category is a category, it's an analog notion to a category where you have object. For each two objects, you have morphisms. And the collection of morphisms is now going to be, say, infinity zero category. So it's going to have many categorical levels. So they have morphism between them and morphism between morphism, etc. But all those levels, except of the first one that we started with, all the other levels are groupoids. All the morphisms are isomorphisms. And this makes the life much easier. And the reason is that we have a very clear example of an infinity groupoid. A very general and very clear example, which is basically a topological space. If we start with topological space, we can consider the same topological space as a groupoid. So the objects will be X, and morphisms will be passes in X, and morphism between morphisms, like this is one morphism, two morphisms will be homotopies in X, etc. Yeah, I did not define what is infinity groupoid, but I, instead of defining it, just give an example. I gave some general intuitive notions that we have objects and morphisms, etc. And here is an example. And now you know what to axiomatize. You want to axiomatize this example. But it's still very hard because, okay, just one example, how I axiomatize it. So they find a better solution. They didn't axiomatize it, they just say this is the only example. Or one of the approaches to higher category theory say it just infinity groupoid is just a topological space, not more, not less. But it's important that you think about the passes as morphisms and the higher things as also morphisms. And so since it is a groupoid and you see that any pass is invertible, any pass you can do it the same pass the other way around. Of course, the composition of two passes will not be identity, but it will be homotopic to identity. Of course, this homotopy is an additional data, but it means that all our errors are invertible errors on all levels. So you should remember somehow that you think about it, that you care about things only up to homotopy, but one of the definition of infinity groupoid is a topological space, and then a possible definition for infinity category in the sense, on this sense, infinity one category, it's what called category enriched over topological spaces. It's a category on which each home have a structure of a topological space, and the composition should be continuous. And basically, this is it. But of course, when you think about it, you have to remember what is equivalence now. So functor between two such categories, or equivalence between two such category, is not an equivalence, an actual equivalence of categories. It's a functor, which is, say, essentially surjective, but it doesn't have to be fully faithful. On each pair of objects, on the homes, it doesn't have to be isomorphism and doesn't have to be homeomorphisms, but it has to be homotopical equivalent because you care about things only up to homotopy. So yes, this is one approach. There are of course many other approaches, and of course each of those approaches have to include much more details in order to have make any sense. It's not enough to define just what is an infinity category. You have to define many basic notions in order to explain what the theory is about. And this is of course not the topic of this course, and I also don't really know it. I know it rather superficially, but I still wanted to give you this glance. This is it. Any questions? Okay, so thank you very much. I will pause the video.